Hello everyone, welcome to online class of electrical machines 1 subject. Previous classes we have seen the three-phase transformer, its construction, types of connection and their comparative features. Today's class I will be telling about parallel operation of single phase and three-phase transformers. So we have covered all these topics, that is what is a transformer, what is the construction, what is the operating principle, equivalent circuit, phasor diagram, voltage regulation, losses efficiency, testing, okay, and separation of hysteresis and eddy current losses. So based on single phase and three phase, they are classified as single phase and three phase transformer. So when you see the operating principle, it is same for both these transformers, that is mutual induction. Transformer works on the principle of mutual induction. So basically there are primary and secondary windings. Two windings will be there in the transformer and they are wound on a common core. Core will be laminated and it is made up of silicon steel material. So to the primary winding we are applying alternating voltage. Alternating voltage will make the current to flow in the coil and flux will be set up in the primary and secondary windings. So whenever there is a change in flux linking with the primary winding, EMF is induced in the primary winding, and when the same flux is linking with the second coil also, so EMF is induced in the second winding also. That is called as mutually induced EMF. The EMF which is induced in the primary winding is self-induced EMF. EMF induced in the secondary is called as mutually induced EMF. The winding to which alternating voltage is applied is called as primary winding, and the winding to which load is applied is called as secondary winding. Okay. So for a small transformer, we can see that we are not providing any uh, uh, oil, transformer oil or any kind of protective material to the small transformer. But for a transformer having bigger rating, tank will be provided, conservator, beather, transformer oil, bushings. Okay, we have seen all this construction part in the previous classes. You can go through them. So then we have seen equivalent circuit. Okay, we are representing all resistances, inductances and reactances in a one circuit diagram for primary and secondary sides, and also we are including no load circuit, equivalent circuit in that. Then we have seen importance of uh, each and every phasor diagram. We have seen what is an ideal transformer. Ideal transformer is one which does not have any iron losses, no winding resistance and no leakage flux. That is, flux will be confined to the core, flux will not leak. Okay. So we have seen ideal transformer on no load, ideal transformer on load, practical transformer on no load, practical transformer on load. We have seen various phasor diagrams or vector diagrams. Very important, students. All these are important points which I am telling here. Voltage regulation we have seen, losses and efficiency. Two types of losses are there, iron and copper losses. No mechanical losses in transformers because there are no rotating parts in a transformer. Only iron and copper losses will be present in the transformer. Then we have seen the condition for maximum efficiency, OCSC test, polarity test, back-to-back test, separation of hysteresis and eddy current losses. Then last class, construction and types of connection of three-phase transformers we have seen. So let us start today's class, parallel operation of single phase and three-phase transformers. Parallel operation of single phase transformers, first we will see. Okay, so by parallel operation of single phase transformer we mean two or more transformers will be connected to the same supply bus bars on the primary side and to the common bus bar or load on the secondary side. So such a requirement is frequently encountered in practice. So parallel operation is required based on our requirement. So what we are doing here, one or two transformers will be connected to the same supply bus bars on the primary side and to the common bus bar or load on the secondary side. So these are the two transformers A and B connected in parallel, which are showing in the figure, and these are primary bus bars, these are secondary bus bars, and these are two transformers A and B. So we are connecting primary of A and B to the primary bus bars, secondary of A and B to the secondary bus bars, and that will be connected to the load. This is parallel connection of parallel single phase transformers. Okay, so while connecting two or more than two transformers in parallel, it is essential that the terminals of similar polarities are joined to the same bus bars. So we will see that also now that there are various conditions for the transformers to be connected in parallel. Okay. So but we have to see that this is very essential that terminals of similar polarities are joined to the same bus bars. Wrong connections will result in a dead short circuit and primary transformers may be damaged unless it is protected by any fuses or circuit breakers. Okay. So we have to make a point that uh, it is very essential that the terminals of similar polarities are joined to the same bus bars. Otherwise, short circuit will occur and primary will get damaged if it is not getting protected by any fuses or circuit breakers. If they are there, then primary will be not short circuit. It will be protected. What is the need of parallel operation in single phase transformer? So there are three principal reasons for connecting transformers in parallel. Firstly, if one transformer fails, continuity of supply can be maintained through other transformers. So this is a primary advantage of connecting transformers in parallel. That is, if one of the transformer fails, then supply will be continued with another transformer. Second advantage, so second need, why we are connecting, okay. Second one is when the load on the substation becomes more than the capacity of the existing transformers, another transformer can be added in parallel. So load is always changing constantly, whether it can be less load or high load, okay. So now whenever load is becoming higher or more, so we can add another transformer in parallel, okay. Say third one, any transformer can be taken out of the circuit for repair or routine maintenance without interrupting the supply to the consumers. Okay. So what we can do whenever they are operating in parallel, we can take out any one transformer which can be taken for repair or any maintenance, routine maintenance without interrupting the supply to the consumers. So these are the three main reasons we are going for a parallel operation of single phase transformer. First one is continuity of supply. Second one is if more load is there, then another transformer can be added in parallel. Third one is if any one transformer is taken out for repair or any maintenance work, then uh, consumers will not get any interruption of the supply even though one of the transformer is taken out for the repair. So some more reasons that necessitate parallel operation of transformer is as follows. First one is non-availability of a single large transformer to meet the total load requirement. Okay, so a single transformer, large transformer cannot, if it is not meeting the load requirement, then at that time we are going for a parallel operation of transformers. So next is power demand might have increased over time necessitating augmentation of the capacity. More transformers connected in parallel will then be pressed into service. Next is to ensure improved reliability. Even if one of the transformers gets into a fault or is taken out for maintenance or repair, load can be continued to be serviced. To reduce spare capacity. If many smaller size transformers are used, one machine can be used as a spare. If only one large machine is feeding the load, spare of similar rating has to be available. So problem of spares becomes more acute with fewer machines in service at a location. So to reduce this more machines, what we are doing, uh, if smaller size transformers are used, one machine can be used. If one large machine is feeding the load, one spare of similar rating has to be available. So the problem of spare becomes more acute with fewer machines in service. When transportation problems limit the installation of large transformers at a site, it may be easier to transport smaller ones to the site and work them in parallel. Okay, so transportation problem also can be avoided with the help of the parallel operation of transformers. So it is easier to transport smaller ones to the site and work them in parallel. Let us see the various conditions for parallel operation of single phase transformer. So this is very important. This can be asked for short questions. What are the various conditions for parallel operation of single phase transformer? In order that the transformers work satisfactorily in parallel, following conditions should be satisfied. So let us see the four conditions. Transformer should be properly connected with regard to their polarities. So first point is that transformer should be properly connected with regard to their polarities. Second one is voltage ratings and voltage ratios of the transformer should be the same. Third point is per unit or percentage impedances of transformer should be equal. Fourth one is reactance or resistance ratios of transformer should be same. So we will see in detail each point. First one, connection with regard to polarity. So these are the correct connections which are shown in the diagram. So the first condition for successful parallel operation of single phase transformer is that transformer should be properly connected with regard to their polarities. So this condition is absolutely essential because wrong connections will lead to the dead short circuit and the primary of the transformer can get damaged if the protection is not provided through fuses and circuit breakers. So the figure on the right hand side is showing the correct method of connecting two single phase transformers in parallel. So we can see here that around the loop formed by the secondaries, two secondary EMFs EA and EB oppose and there will be no circulating current. So EA and EB are opposing and there will be no circulating current. So figure on the right hand side is showing the wrong method of connecting two single phase in parallel. Here two secondaries will be so connected that their EMFs are additive. EA and EB are additive. In the previous diagram we have seen their polarities was opposite. So EA and EB were opposing. But now E and EB are additive. So this may lead to short circuiting conditions and very large circulating current will flow in the loop which is formed by the two secondaries. So such a condition can damage the transformers unless they are protected by fuses and circuit breakers. So connection should be proper with regard to the polarity. This is the first condition for the parallel operation of transformer. Second one, same voltage rating and voltage ratio. So next condition for parallel operation of single phase transformer is same voltage rating and voltage ratio. This condition is desirable for the satisfactory parallel operation of transformers. If this condition is not met, secondary EMFs will not be equal and there will be circulating current in the loop which is formed by the secondaries and which will result in unsatisfactory parallel operation of transformer. So what is the second condition? Voltage rating and voltage ratio should be same. Okay, if it is not same, then there will be some circulating current in the loop which is formed by the secondaries and it will result in the unsatisfactory parallel operation of transformers. So we will see here in the diagram, let us consider a single phase transformer A and B operating in parallel. So there are two transformers A and B operating in parallel here. Let E and EB be their no load secondary voltages and ZA and ZB be their impedances referred to secondary. So EA, EB is the no load secondary voltages, ZA, ZB are the impedances referred to secondary. So at no load, circulating current in the loop formed by the secondaries is IC equal to EA minus EB by ZA plus ZB. We are assuming here that EA is greater than EB. So even a small difference in the induced secondary voltage can cause a large circulating current in the secondary loop because impedances of transformers are small. So the secondary circulating current will cause current to be drawn from the supply by primary of each transformer. So because of this secondary circulating current, more current will be taken by the primary of each transformer and these currents will cause copper losses in both primary and secondary and this will create heating with no useful output. Okay. So what is happening now? The transformer gets heated up and with it is not giving any useful output because copper losses are occurring in both primary and secondary side. So when the load is connected to the system, the circulating current will tend to produce unequal loading conditions. That is, transformers will not share the load according to their kVA ratings because circulating current will tend to make the terminal voltages of the same value for both the transformers. Therefore, transformer with a smaller voltage ratio will tend to carry more than its proper share of the load. One transformer would tend to become overloaded than the other and the system could not be loaded to the summation of transformer readings without overloading one transformer. So, this is very important to make the voltage ratio, voltage rating and voltage ratio to be same. Next is another condition for parallel operation of a single phase transformer is all transformers should have equal percentage impedance. So this condition is also desirable for proper parallel operation of single phase transformers. If this condition is not met, transformers will not share the load according to their kVA ratings. Okay, so equal percentage impedance should be there for the parallel operation of single phase transformers and if this condition is not met, transformers will not share the load according to their kVA ratings. Sometimes this condition is not fulfilled by the design of the transformers. In that case, it can be corrected by inserting proper amount of resistance or reactance or both in series with either primary or secondary circuits of the transformers where the impedance is below the value required to fulfill this condition. Next condition for the transformers to be in parallel is same reactance or resistance ratio. If the reactance or resistance ratios of the two transformers are not equal, power factor of the load supplied by the transformers will not be equal. Or in other words, we can say that one transformer will be operating with a higher and the other will be operating with a lower power factor than that of the load. Equal percentage impedance, that is condition 3, is much more important than the same reactance or resistance ratio, that is condition 4. Considerable deviation from same reactance or resistance ratio will result in only a small reduction in the satisfactory degree of operation. So when desired, condition 4 also may be improved by inserting external impedance of proper value. So let us see how transformers works when they are connected in parallel. So parallel operation of a single phase transformer means that two or more transformers having same polarities, same turn ratio, same phase sequence and same voltage ratio are connected in parallel with each other. So circuit diagram of two single phase transformers A and B connected in parallel is shown in the figure. So they have to meet all the conditions which I have said previously, that is they should have the same polarities, same turn ratios, same phase sequence and same voltage ratio. So they are connected in parallel now, the transformers A and B. Let A1 is the turn ratio of transformer A, A2 is the turn ratio of transformer B, ZA is the equivalent impedance of transformer A referred to secondary, ZB is the equivalent impedance of transformer B referred to secondary, ZL is the load impedance across the secondary, IA is the current supplied to the load by the secondary of transformer A, IB is the current supplied to the load by the secondary of transformer B, VL is the secondary load voltage, IL is the load current. So when we apply Kirchhoff's current law to the circuit, IA plus IB equal to IL, and by Kirchhoff's voltage law we can write VL is equal to V1 by A1 minus IAZA and VL is equal to V1 by A2 minus IBZB. So these equations are 1, 2, 3. Now putting the value of IB from equation 1 in equation 3, we will get VL is equal to V1 by A2 minus IL minus IA into ZB. Solving these two equations, second and fourth, we will get the values of IA and IB respectively. The current IA and IB have two components. First component represents the transformer share of the load currents and the second component is the circulating current in the secondary windings of the single phase transformer. The undesirable effects of the circulating currents are as follows. They will increase the copper loss. So because of this circulating currents, copper losses will increase and circulating current overloads the one transformer and reduce the permissible load kVA. Equal voltage ratio. In order to eliminate circulating currents, voltage ratios must be identical. That is, A1 should be equal to A2. So when we under this condition, IA and IB will become now IA equal to ZB IL by ZA plus ZB, IB equal to ZA IL by ZA plus ZB. Equating these two equations, we will get IA by IB equal to ZB by ZA. And from this equation, it is clear that transformer currents are inversely proportional to the transformer impedance. Thus, for the efficient parallel operation of two single phase transformers, potential differences at full load across the transformer internal impedance should be equal. So this condition ensures that load sharing between the two single phase transformer is according to the rating of each transformer. If the per unit equivalent impedance are not equal, then transformer will not share the load in proportion to their kVA ratings. As a result, overall rating of the transformer bank will be reduced. Now we can write equation 9 as IAZA equal to IPZB also. So current in this equation 7 and 8 will be changed into volt amperes by multiplying these two equations by common load voltage VL. So we know that total load in volt amperes is SL equal to VL IL. So in volt ampere of transformer A will be SA equal to VL IA. Similarly, volt ampere of transformer B will be SB equal to VL IB. So various equations can be written now. SA equal to Z in place of VL, ZB by ZA plus ZB into SL, and SB can be written as ZA by ZA plus ZB into SL. So when we equate these two equations, SA by SB equal to ZB by ZA, and this equation is telling us that volt ampere load on each single phase transformer is inversely proportional to its impedance. So to share the load in proportion to the ratings, transformer should have the impedance which is inversely proportional to their ratings. So parallel operation of three-phase transformer, now we are going to see. So parallel operation of three-phase transformer is very common in three-phase power generation, transmission and distribution. It is advantageous to use two or more transformer units in parallel instead of using a single large unit. This offers flexibility for maintenance as well as operation. So what we are doing, instead of using a single large unit, we are using two or more transformer units which are connected in parallel. And this will offer flexibility for maintenance as well as operation. So as I said earlier, three important uses or needs of parallel operation. First one is that uh, if one of the transformer fails, then other two can be working in giving the continuous supply to the consumers. And second one will be what they can be if at all load is increased, then we can add extra transformer in parallel. Third one is that if they are taken out for any repair or routine checks, okay, so easily it can be taken out. Other two will be working, two or three, whatever it may be, other transformers can be working, and the transformer to which we have to take for repair can be taken out easily. So this will offer flexibility for maintenance as well as the operation. Advantages of parallel operation of three-phase transformers. It increases the reliability of supply system. So now we will understand how this happens. Suppose a fault occurs in any one of the transformer unit. In such case, faulty transformer may be taken out of service while the remaining transformers will feed the power supply. Whenever a fault is occurring on any one of the transformer, that faulted transformer is taken out and the remaining transformers will feed the power supply. If there were only one large transformer unit installed for supplying the load, then supply to the entire load will be interrupted during breakdown of the transformer. Thus, reliability of supply system will be increased by parallel operation of transformer. So, in this way, we are saying that the reliability of the supply system is increased by using parallel operation of transformer. Even if the fault is occurring on any one transformer, so uh, remaining transformers will be feeding the supply. If at all, if it is not in parallel condition, if the transformers are not operating in parallel, at that time what will happen? One large transformer unit, whatever is there, which is installed for supplying the load, then to supply the entire load will be interrupted, and power will not be continuously given to the consumer there because of the breakdown of the transformer. So reliability of supply system can be increased by parallel operation of transformers. Size of the transformer increases with the increase of its rating. Therefore, larger transformer will be bigger in size and its transportation from manufacturer to the site will be difficult. Whereas transportation and installation of small site transformers will be comparatively easy. So instead of a very large unit uh, and getting it transported from one site, from the site to the other places, it will be very difficult, whereas transportation and installation of small size transformers will be comparatively easy. Maintenance opportunity in case of parallel operation is increased. One or more transformers may be taken under maintenance while the remaining transformers will supply the load at reduced power. Now let us see the condition for parallel operation of three-phase transformers. Following are the necessary conditions for parallel operation of three-phase transformers. First one is line voltage ratio of the transformers must be same. Second is transformers should have equal per unit leakage impedance. Third is the ratio of equivalent leakage reactance to equivalent resistance should be same for all the transformers. For this, transformer should have the same polarity. So similar to what we have seen for single phase transformers, almost they are same here. So what are the necessary conditions? First one is line voltage ratio of transformer must be same. Transformer should have equal per unit leakage impedance. Ratio of equivalent leakage reactance to equivalent resistance should be same. And transformer should have the same polarity. So these four conditions are also applicable for parallel operation of single phase transformers. Apart from the above four conditions, there exist two more conditions which should be fulfilled for the parallel operation of three phase transformers. So what are they? We will see now. So the relative phase displacement between the secondary line voltages of all transformers should be 0. This means that transformers to be connected in parallel must belong to same group number like YY0, DD0 belong to same group number, group 1. Phase sequence of secondary line voltages of all transformers should be same. There may rise several questions in mind at this point of time, though I can't solve, but so why relative phase displacement between the secondary line voltages should be 0? Or what would happen if transformers of different group numbers are connected in parallel? So let us assume that two transformers of different group numbers are connected in parallel as shown in the figure. So secondary line voltages of these transformers will not be in phase, rather they will be displaced from each other as shown in the figure. Voltage across which S1, S2, S3 will be developed due to this displacement in secondary voltages. Voltage across switches S1, S2 and S3 will be equal to the length of phasor joining A2, A2 dash, B2, B2 dash and C2, C2 dash respectively. Due to this voltage, when these switches are closed, a large circulating current will start flowing through the secondary winding, and this can damage the transformer. So whenever you hear the word circulating current, then you understand here that the transformer is getting damaged. Okay, therefore it is essential that transformers belong to the same group number so that the relative phase displacement between the secondary line voltages is 0. However, the transformers of group numbers 3 and 4 can be successfully operated in parallel. Next question which can be arised is why phase sequence should be equal for parallel operation of three phase transformers. Phase sequence of secondary line voltages of all the transformers should be same. If the phase sequence is same, there will not be any voltage across the switches S1, S2 and S3. However, an improper phase sequence may result in complete damage of the transformer. Let us consider the figure below. So in the left figure, phase sequence of secondary line voltage of both the transformers are correct. Therefore, zero voltage will be developed across switch S1, S2, S3. But in right figure, phase sequence is reversed for the second transformer. You can see here. Here it is A2 dash, B2 dash, C2 dash, A2, B2, C2. Here it is A2, B2, C2, and this one for secondary it is A2 dash, C2 dash, B2 dash. So for second phase sequence is reversed. So under this case, no voltage will be there across S1, but voltage equal to line voltage C2 B2 dash and B2 C2 dash will be developed across the switches S2 and S3. These switches may not be designed to withstand this voltage. Therefore, parallel operation is not possible. Thank you everyone for watching the video. So I hope today's class is clear to everyone. If you have any doubts, you can ask me, students. Give your attendance in comment section. Subscribe to all the YouTube channels of all the faculty members who are taking your subject, so that whenever a new video is made, you will get a notification. So however, I will complete the syllabus in still 2 more classes are required for me uh, to complete the syllabus. Thank you everyone for watching the video.